Yes? Okay, good. Okay, we're going to get this. Welcome, everyone. We're so excited to have you here. I'm Jen Glass, and I have the great honor of introducing our first keynote speaker, who is Dr. Reva Kay Williams. And she is our nation's first Black female theoretical astrophysicist. She's originally from Memphis, Tennessee, raised in Chicago from the age of 6. Dr. Williams earned degrees in liberal arts from Malcolm X College and in astronomy from Northwestern University. She received her PhD in astrophysics from Indiana University, followed by a Ford Foundation postdoctoral fellowship at the University of Florida. She went on to hold astrophysics appointments at North Carolina A&T State University and Bennett College, where she was also the director of the Center for Women in Science. Since 2008, Dr. Williams has been a research professor of astrophysics at the University of Toledo. She is an expert on black hole physics and was the first person to successfully work out the Penrose mechanism of energy from rotating black holes using Einstein's general theory of relativity. It is a great honor to welcome Dr. Williams as our opening keynote speaker at the 2022 Astrobiology Science Conference, where our theme this year is Origins and Exploration, from Stars to Cells. Carl Sagan famously said, "We are made of star stuff." And Dr. Williams will be kicking off our conference by taking us to the birthplaces of the elements, the supermassive stars that seed the elements for life in the universe. Please give a warm welcome to our first keynote speaker, Dr. Reva Kay Williams.
Good evening. I'm going to talk about the formation of supermassive stars in the early universe and their evolution to quasars. And in this process, I will talk about how these stars release stardust into the universe, which became the seeds of life for our formation and the heavy elements that formed our planet. Now, many of you, I'm sure, recognize these scientists. They are Sir Isaac Newton and Albert Einstein. Not only did these scientists, with their laws and theories of gravity, lead us to the knowledge of black holes, particularly Einstein, but on a more personal level, these scientists are the reason I'm here today giving this talk. That is, early on in my quest to find out which area of science I wanted to pursue as a career, when I was first introduced to these scientists' laws and theories of gravity and motion, I fell in love with the physics. And that basically sealed my faith in my becoming an astrophysicist, one that studies the physics of the universe. My agenda would be the following. First, I will talk about the origin of the universe in the beginning, that is the Big Bang. Then I would talk about the formation and evolution of supermassive stars. Next, I would talk about how these supermassive stars can transform, and I'll explain that, to rotating black holes and then to quasars. Quasars, I will talk how they evolved to galaxies and then our solar system and to humans. And next, finally, I will conclude. So the origin of the universe in the beginning. First, I want to talk about my beginning. Now, so that I can keep within the time limit, I had to write it down so I wouldn't go off on a tangent. So let me start from the beginning. After high school, while working at an insurance company as a claims adjuster for 2 years, I got a calling from God to go back to school. I quit my job and enrolled in Malcolm X College the following fall semester. I knew I wanted to be a scientist, and I read books on how to become a scientist. In one book, it gave a summary of different fields of study of interest. And when I came to cosmology, the study of the universe as a whole, I knew that this was my calling. For I believe that God created the universe, and I wanted to find out how he did it scientifically so that I can tell people. Along the way, I fell in love with the laws and theories of Newton and Einstein. This was before I knew that they were two of the greatest scientists to live. Neither had it clicked that both worked on gravity. This was at Malcolm X College. But it was clear to me that their laws of motion appeared to apply to our lives, and I wanted to know more about their lives. So when I got to Northwestern University, I had the opportunity to do a term paper on Isaac Newton's life and a book report on the universe and Dr. Einstein by Lincoln Barnett. When I read Einstein was working on the unified field theory, at least to unify gravity and electricity and magnetism when he passed away, I then felt that it was my duty to pick up where he left off. I then focused my studies on Einstein's theory. And that was when I was a sophomore at Northwestern University. Now, having said that, I present to you my scientific journey and the knowledge I acquired along the way. First, I briefly talk about Newton's three laws of motion, which he introduced in 1687. The first law is the law of inertia, that it governs the motion in our universe. So it says that once an object is at rest or in motion at a constant velocity, it will continue at rest or in a constant velocity unless acted upon by some outside force, and that's some kind of change. The second law is force equal to mass times acceleration. Our mass is the same wherever we go. When we go to the moon, on Earth, it's the same. And so the force we have is our mass times our acceleration, our change. The third law, and I'm sure everyone can relate to this one or recognize this one, it says for every action, there's an equal and opposite reaction. This is a biblical law. You reap what you sow. We always say what goes around comes around. And back in the day, we used to say every dog has his day. And the law of gravity says that the force is greater between two masses if the distance is close. So now just briefly stating what Einstein's general theory of relativity states, that was introduced in 1915. Einstein's theory describes motion in a gravitational field. This is his general theory of relativity. His special theory of relativity just describes relativistic motion. So the general theory describes gravitation. So it describes motion in a gravitational field. It shows that clocks run slower in a gravitational field, and it shows that space-time is curved around a massive body. So I'm sure many of you all have seen this rubber sheet analogy for gravity, and this is the way Einstein describes gravity. So if you have a rubber sheet and you put a large mass there, then it's going to make any objects on that sheet fall towards it. And so that's what he attributes to gravity. Whereas Isaac Newton's gravity is like force at a distance. So this is just an image of the book that basically changed my life. So now we can begin with the origin of the universe. So around 13.7 billion years ago, there exists matter that was mass, energy, and space-time bound together by gravity at a point. It appeared that this matter, when I talk about the Big Bang, came out of nowhere. This matter had infinite energy and infinite density, more energy than we can imagine. And there was a cataclysmic explosion by some mechanism, and it converted this matter to energy, expanding photons traveling the speed of light. I need to get my, this is actually supposed to be a movie. Okay, well, let me just go on. And God said, let there be light. And that was light. And that's the Big Bang. This matter began expanding outward at the speed of light. And it was governed by Einstein's um, special theory of relativity energy equation, or energy mass conversion equation, E is equal to mc squared. And the light expanding outward was governed by Maxwellian, Maxwell's, I'm sorry, Maxwell's equations for for electricity and magnetism. And so that was the process of the Big Bang. The matter that I described before the Big Bang, all of the fundamental forces were unified. And immediately after that, they were still unified. That is, the fundamental forces are electricity and magnetism that governs the electron outside the nucleus, and it holds the atom together. And then the nuclear forces, the weak forces, which governs radioactive decay, and then the strong forces, which holds the nucleus together because of the charged particles. And then you have gravity, basically by itself. Now, Einstein wanted to at least unify electricity and magnetism and gravity. After the Big Bang, from about 10 seconds to 20 minutes, you had Big Bang nuclear synthesis, where the lighter elements were formed. In mass abundance, about 75% of hydrogen was formed, about 25% of the helium was formed, and some deuterium and helium-3, and a small amount of lithium. So now we're going to talk about the formation and evolution of supermassive stars. First again, I want to give you a little history about the supermassive stars. Trying to get rid of this. Bear with me. Anyway, I want to first tell about the history, my history of studying supermassive stars. My desire has always been to contribute to science. So the summer before graduate school, I predicted that supermassive stars were quasars. I didn't call them supermassive stars, I just said gigantic stars. And so I continued working on this idea in graduate school, and I was excited to find that Nobel Prize laureate Williams Fowler once believed as I did. So I started duplicating his model, preparing as part of my dissertation, or to gain knowledge to do my dissertation. So when I got to the part to generate the jets, and he was saying by some non-thermal oscillation, I wrote him a letter and asked him why he no longer worked with them. This was at the advice of my advisor. And he wrote me back stating that supermassive stars did not live long enough to explain quasars, but that black holes did. And I knew, and also he said that supermassive stars could be the progenitors of quasars. So I knew that the only way to go was to study black holes. So my focus became supermassive black holes to explain quasars, in which Einstein's theory of gravity or general relativity must be used. So now I had returned back to general relativity. So when the matter from the Big Bang, after it exploded, it began to expand outward and it cooled. The original temperature was about 10 to the 15 Kelvin. And so as this matter, excuse me, as this matter cooled, then atoms were able to form, and hydrogen from the nuclear body, the Big Bang nuclear synthesis was able to form. And so this hydrogen, once the hydrogen atom formed, then the universe became transparent. And so as it continued to expand and cool, molecular clouds were able to form. And embedded in these molecular clouds were dense instability regions where gravity was able to contract. And so between 100 million and 250 million years after the Big Bang, these first stars formed, and they had masses of the order of 1 million solar masses, and their lifetimes would be about 300,000 years. Now, when the more massive a star is, the shorter its lifetime. So this is why these stars didn't live very long, in which they were converting hydrogen to helium in their cores. Whereas our sun has a lifetime of 10 billion years, and that's because of the sun's small mass. So I want to say something now about the evolution to the stellar onion skin layers of nuclear reactions. And this process contained the seeds of life. And these seeds of life were interior to the supermassive star. So after the supermassive star had exhausted its available hydrogen, in which it was converting hydrogen into helium and radiating X-rays at its core by nuclear fusion reactions, the supermassive star became unstable to gravity and started to collapse. And as the core collapsed, it heated, developing shells of nuclear reactions, which were the building blocks of life. But these building blocks of life were interior to the supermassive star. So this process continued, burning heavy elements at its core until it reached the element of iron, which is the most stable element. And this was the end game of stellar nuclear fusions. So this is a diagram of the onion layers, the onion skin layers. So here you have a hydrogen envelope, and then here you have the hydrogen that's burning outside the core. That was the initial hydrogen, and it was fusing into helium. Then once so you have a helium core, then it starts to contract under gravity because there are no nuclear reactions, and then helium starts to fuse. And after that, then the helium exhausts its available energy or matter or hydrogen or helium. And then the core starts to flap under gravity, and it heats again, and then you have carbon beginning to burn from the helium fusion. And then you have the oxygen fusion, and this continues, and then you have magnesium, neon, and oxygen fusion. Then you have silicon sulfur fusion, and then you have the iron core. So once it reaches the iron core, then gravity takes over. And I'm trying to get rid of this. Any suggestions? Oh, I got it. Okay. So the iron core, not being able to undergo nuclear reactions to support the outer layers, becomes unstable and collapses violently under gravity, resulting in a supernova explosion. And this is how stardust is ejected into the universe, which is the seeds of light. So this is a movie of a supernova explosion. And so here, this is the star is well, the core is here, and then the outer layers are blown off because of the gravitational energy released because of the violent collapse. So once the core starts to collapse, because of the mass of the star, nothing can halt the collapse. And so it continues to collapse under gravity, and the gravitational force increases until light can no longer escape. And that surface is called the event horizon, where anything inside the event horizon cannot escape unless it's traveling greater than the speed of light. And Einstein's theory tells us that no matter can travel greater than the speed of light. So that light is trapped, and we do not know what really happens to that core because our physics, Einstein's physics, appear to break down there, and we need a theory for quantum gravity to describe what's happening to that core. So you see how the matter is being ejected. These are actually observations of supernovae. This is one. Another one. So now you have this matter out in the universe. The four most abundant elements in the human body are hydrogen, carbon, oxygen, and nitrogen. They are all made inside of stars. So the collapsed core leads to the formation of a supermassive black hole. In the early universe, the density of these supermassive black holes or supermassive stars, left that off, they are now black hole systems, would have been large. The density of the early universe would have been large, and their gravitational interactions through collisions would have been frequent, as observations indicate. Now, an important characteristic about black holes is that when they collide, they merge into one black hole and of greater mass, and they release a tremendous amount of energy in the form of gravitational waves. So recently, well, the LIGO, in which Kip Thorne won a Nobel Prize for, they were able to observe these gravitational waves from the merging of two black holes. This is a picture of observations of a cluster of galaxies. Now, I showed this because you can imagine, like, when the universe was dense, that these objects, these newly formed supermassive black holes, that it was hard, it was hard to think that they did not undergo several collisions, although some probably didn't undergo them, or they underwent collisions with objects that were smaller than their mass, and therefore they couldn't really disrupt the systems, the black hole system. I'll explain that in a minute. Okay, so now we're at the point to where the supermassive stars have evolved to supermassive rotating black holes. And now I want to talk about how these supermassive black holes evolved to quasars. So matter injected in the supernova explosion could serve as an accretion disk for the matter. An accretion disk forms when a black hole draws matter inward, and accretion disk is a plane. And so the accretion disk forms because that matter, instead of it, say, falling in spherically, it falls in a plane because of the angular momentum of that matter. And most matter in the universe has angular momentum. And so you have the the black hole and the accretion disk. Now, the accretion disk is normally, well, it's a thin disk, and so it's relatively cool. But when the particles energy reaches 17 keV, due to thermal and density instabilities that naturally occur in the initial thin disk, the target orbits inside the ergosphere can be populated to activate the Penrose mechanism. And I refer to it as the Penrose-Williams mechanism because other people were working on the Penrose mechanism, and I wanted to distinguish my model because they were having problems with theirs. So, it activates the Penrose mechanism, which causes the formation of jets. And this is the birth of a quasar, which is the most distant object and the most energetic object in our universe. So I want to say something about the Penrose mechanism. In 1969, Roger Penrose proposed a way to extract particle energy from the ergosphere called the Penrose mechanism. The ergosphere, meaning energy sphere, is a region that one encounters as, say, a particle is falling into the event horizon or toward the event horizon. It encounters the ergosphere. The ergosphere is a region where the angular momentum or the rotation of the black hole drags space-time around, and they call that inertia frame dragging. So it drags space-time around, and as it's dragging it, the particles that are inside the ergosphere, they acquire a large energy because of the rotation. So once inside the ergosphere, if you could have a particle come from outside and collide with one of these highly energetic particles, then it could take the energy back out. And so this is Penrose classical process where he proposed in like a paragraph or so that a particle could break apart, one becomes trapped and the other one escapes. The one that becomes trapped can acquire a negative energy. Now, only inside the ergosphere can a particle have negative energy. This particle cannot escape back out. But what happens is that, try to move this. You all probably can see it. Okay, that's what I wanted to say. So due to conservation of energy, the initial particle has energy E1. So conservation of energy says that E1 is going to equal to E2 plus E3. So if you solve for E3, which is the escaping particle, then you have E1 minus E2. But if E2 is negative, then E3 is the absolute value. E3 is equal to E1 plus the absolute value of E2, which is going to be positive. And E3 would escape with more energy than E1 because it would escape with the E1 energy plus the positive or the absolute value of E2. And this is how rotational energy is extracted from the black hole by the Penrose mechanism. Now, the Penrose mechanism, the classical process, it was shown that the efficiency was very low and that the scatterings had to be relativistic. So in my analysis of the Penrose mechanism, I was able to obtain the four momentum of the particles escaping, which is the energy and the three space components. So I would have the energy and also the structure of the particles escaping. And the structure shows that it's a jet. And I'll talk more about the structure of that jet. So I did Penrose Compton scattering, where I had an electron in an orbit inside the ergosphere. A photon collides with this electron and send the electron on a negative energy orbit or a lower energy orbit, and it escaped the photon escaped with more energy than it initially had going in. Another process, which was very important, I did was the Penrose pair production, where you have two gamma rays and they collide and form electron-positron pairs. Now, this was done at the photon orbit. So here, before you have a photon in orbit, at the photon orbit, another lower energy photon comes in, they pair produce. On the average, one of the electrons would eventually fall into the event horizon, and the other electron escape. Also, what I found was that first I had to get the particles out, because other models that I worked with, they didn't, like the Blanchard model, it didn't create the particles. And so once I got the particles out, I was going to use a Blanchard type model, which used electromagnetism to accelerate the jets. I was going to use that model, but then as I further investigated what my particles were doing, my particles were escaping in the form of vertical polar jets. And I'll show you that in a moment. But no, items 1, 2, and 3 are all consistent with observations. So this is just a diagram of what my model is doing. So the Penrose-Williams model is a 4-dimensional general relativistic mathematical model, which uses space-time frame dragging. And again, and so doing this model, I overcame some of the problems associated with the popular Blanchard type model. My model is self-consistent, and it constitutes a complete theory to extract energy from a black hole. So this is the thin accretion disk, and due to instabilities, the iron corona forms a hot iron corona with temperatures of the order of 10 to the 12th Kelvin. So this is the ergosphere. So once I perform those scattering processes that I just described, the particles escape along these vertical orbits, and this is plasma. So as they're escaping, they generate a intrinsic magnetic field, and these are the magnetic field lines. So the Penrose mechanism basically did everything that we observe quasars to be doing in active galactic nuclei. This is a picture of active galactic nuclei. We will see that they are basically quasars that have evolved, and some of their available energy has been depleted from the accretion disk. And so they are in between, say, our quiescent galaxy, the Milky Way, and then quasars. And here you can see the jets extending out, where these jets extend outward to kiloparsec distances, very far away from the central black hole, a rotating black hole. This is another, this is actually an observation of the jet and then the core. Also, in the early dense universe, when these quasars first turn on, or even later on, since these jets extend out to kiloparsec distances, they can initiate star formation in other galaxies, as well as the energy that is released in their own galaxy. And this would lead to a period in which cosmic time, a period in cosmic time of intense star formation. This is an artist's conception of an active galactic nuclei. This is actually an observation, and here you see the jet. And this jet is, you only see one side because it's due to Doppler boosting, where the other jet has been redshifted or shifted to a lower energy, and so we can't see it. And also, this one-sided jet could also be contributed to what we call the gravitomagnetic field associated with a rotating black hole. And it's also possible that one-sided jets are produced in this way also. This is the artist. I'm sorry. Let me see that. This is an artist drawing of space-time being dragged around, and then here you see the jet is being emitted in the polar direction. This is another drawing. This is based on this observation. And so here you see the accretion disk. Now, these lines, according to the Penrose mechanism, these are particles in those vertical orbits and with the magnetic field here. Now, probably further outward, further out, the beyond the frame dragging effect, then the particle's angular momentum no doubt turns into linear momentum. So the particles would be escaping along the pole, and electromagnetism tells us that the magnetic field would be in this helical shape, but this would be outside the frame dragging effect. This is an observation of the first observation of a black hole. And this is the black hole shadow. And this was taken by the Event Horizon Telescope. So here, this matter is coming, this light is coming from the photon orbit and is produced by synchrotron radiation produced by electron-positron pairs. And the Penrose mechanism first predicted these this radiation at the photon orbit. This is the Event Horizon Telescope observation, and these are polarized. This is a polarization observation. According to the Penrose mechanism, these are particle orbits that are emitting synchrotron radiation from the magnetic field. So from these observations, it appears that the Penrose mechanism is being confirmed. So now, we want to go from quasars to galaxies. So quasars will evolve into galaxies. So over time, quasars evolve into nearby galaxies as we know them today. Some spiral, some elliptical, and some in between. We observed, I think it was in 1994, with the Hubble telescope, that most galaxies have black holes at the center. So now, it appears that the original primordial supermassive black holes that evolved directly from the supermassive stars that became quasars and avoided colliding with neighboring supermassive black holes. After their quasar phase, it appears that they evolved into spiral-shaped galaxies like our Milky Way. So they basically retain that original structure from that supernova explosion, and then the black hole forming and the jets turning on. And so they would still have that spiral shape or that planar structure because they had not interacted much with neighboring supermassive black holes. So this is pictures of galaxies that look like our Milky Way galaxy. So the black hole would be in the center. These stars, their jets, because perhaps they didn't have enough matter, the jets are quiescent in these stars, in these galaxies, like our Milky Way galaxy. Now, on the other hand, it appears that the supermassive black holes / quasars that collided with neighboring supermassive black holes and merged, that their planar orbits were scattered into random three-dimensional orbits, with many of the orbits being elongated And these appear to have evolved into elliptical galaxies in our present epoch, or our present time. So remember that the further out we look in the universe, the further back in time we're looking, because light has a finite speed. So say, for example, you're looking at a quasar that's 1 billion light years away. And because it takes light a time to reach us, we're looking at that star or at that quasar or galaxy the way it looked 1 billion years ago. This is a picture of an observation of an elliptical galaxy. So you see it's different from the spiral-shaped galaxy. And its angular momentum has been scattered into these elongated orbits, whereas the spiral-shaped orbit, it appears to have retained its angular momentum, or the orbit's angular momentum. So this is a diagram showing spiral galaxies, okay? And these are elliptical galaxies. Now we observe that the elliptical galaxies seem to be associated with powerful jets. And that's probably because these objects, when they combine, so every time a black hole collided and combined, the masses became larger, and therefore it had more matter to accrete. The accretion rate became larger, and so therefore they will give off more energy than these type, like our galaxy. And these are the irregular galaxies, when I said in between. So within these now quiescent galaxies, like our Milky Way, our solar system was able to form, and humans were formed from the original stardust of the primordial supermassive stars. Here's a diagram, picture of our planets, the sun, and our planets out to Neptune. And notice Pluto is not there because Pluto had been downgraded to a dwarf planet. So conclusions. I have shown in this talk, by following the evolution of supermassive stars over cosmic time, that we are made from star stuff, as Carl Sagan would say. And here we started from the Big Bang. This is the region that the cosmic time in which first stars formed. These stars evolved into quasars, black holes, and then quasars, in which the jets turn on. And the matter that the jet was feeding off of eventually became stars in our galaxies that were initiated or activated by the supermassive rotating black hole and its jet. And as time evolved, the energy that allowed the quasar to form has been depleted, and now these objects, as they evolve, you have active galactic nuclei, and then as they evolve to our present epoch, then you have quiescent galaxies like our Milky Way galaxy. Thank you very much. I'll end with that.
Thank you. Thank you, Dr. Williams. I'm now very pleased to open the floor to questions for our first keynote. And you may come up to the microphones, which are right here, and there's another one right there. Yes, I see our first questioner. Go ahead. Is that Tony?
Yes, it is. I am Anthony Bernetti here at Georgia Tech. Thanks so much for being able to talk to us. And I have a super naive question from a biologist, just about something about the Penrose Williams process you were talking about. I was just wondering if that is that process just sort of, I'm trying to figure out how to ask the question. Is it just sort of a pipe you can shove matter into and it just goes through, or is once it gets established, is there sort of a ongoing process that's like an engine that moves it through, or is it just something that happens no matter what? Is there a state that the system needs to be in to keep things moving, or is it just something that no matter what, when you drop something into it, it happens?
Okay. Well, actually, it's a state that has to satisfy certain conditions. And when I stated that well, I didn't fully state it, that the accretion disk, the thin accretion disk, it normally has a energy that's 3.5 electron volts. But once it becomes unstable due to thermal and density instabilities, where the disk heats up, then it has to heat up to a temperature of 17, energy or temperature of 17 electron, 17 kilo electron volts. And once that happens, then the orbits inside the ergosphere can be populated. Otherwise, if the orbits can't be populated, then the matter is just accreted into the event horizon.
Okay.
But right, so those orbits have to be populated first. Okay,
Right.
and I was going to say, and the instability is something that naturally occurs in the thin disk. It's naturally unstable, where it goes from thin disk to iron corona, where you have that iron corona over it, and then it can oscillate between the two.
Right.
And again, let me just say this, that once in order for the process to take place, it has to have accretion disk. Okay, it has to have matter to be drawn in. If once the accretion disk has been depleted, then the black hole becomes quiescent, and like our black hole at the center of the Milky Way galaxy. But then if say a star cluster comes by and tidal force is disrupted, then that matter would fall in, the Penrose mechanism would turn on, the jets would occur, and then once that matter is depleted, then the black hole basically turns off, or the Penrose mechanism turns off. Okay.
Thank you so much.
You're welcome.
Great. Okay, more questions. Just come on up to the mic. There's got to be more questions. Well, I'll let you. Oh, I see another question coming up. Great. And in the meanwhile, I guess I actually can't see the questions online, Marco. So if you want to read any of them out, that'd be great. We don't have any yet. Okay. All right, but we have one here. Here, go ahead.
Hi there. This is Aaron Gronstall from the Astrobiology Program Office. I'm a biologist, so this is all way outside my field. But I was just wondering if you kind of follow that process further along to sort of solar system stellar system formation and the formation of planets. Is there anything that would be different about planetary formation in an elliptical galaxy versus a spiral galaxy and that sort of thing?
Well, in the elliptical galaxy, you have these elongated orbits, okay, and that means like these elliptical orbits that are elongated. So that would be something different from our sun and its solar system. So I don't, our observations, we haven't been able to detect any, any planets about a elliptical galaxy. But the elliptical galaxy, like, it doesn't have much star formation because these are like older stars. Whereas the spiral shaped galaxy, it has gas and dust in its disk, and you have star formation regions. But the elliptical galaxy, they have, very little, if any, star formation region. But that's an interesting question, because now I'm going to try to investigate it and see, if there's something to that, because, it may be. that they have planned. So I'll have to investigate that. But thank you for the question.
Yeah, thank you.
Great. Wonderful. Okay, more questions. While you're all thinking of questions, I will ask one myself. Dr. Williams, that was a beautiful talk. Thank you, first of all. And
Thank you.
and secondly, and it was so understandable for even me, who's just a geologist. So thank you for that. And could you tell us anything more about your own story? I love the portions about your story. First of all, thank you for sharing those. And do you want to share anything else about your story, and especially what excites you most going forward?
Well, when I went to Northwestern, and I found out about what Einstein was trying to do. So I started taking classes that I wanted to unify the forces also. So I thought about when I was a sophomore, I thought about, okay, everything spins in the universe. That's the common, spin. Everything spins in the universe. And so that was as far as I could go. But then I kept investigating, and I thought about, I was studying for the graduate, the GRE, right? GRE exam my senior year. And it was saying, they said, we understand the effects of gravity. We don't know what gravity is. And so I started thinking okay, what is gravity? Now, remember, I was looking for the unified field theory. And so and then I thought about what Einstein was doing. He was trying to unify the forces. So I worked with the forces, and I actually got the gravitational force, the gravitational acceleration proportional to the magnetic current. And so that was, a really breakthrough. So I started working with it, and I was able to calculate, given the spin and the gravitational acceleration, I was able to calculate the magnetic field of the sun, a neutron star, and a black hole. And when I got to graduate school, I entered my theory into a gravitational paper writing contest that they had advertised on the bulletin board. I didn't realize that people like Penrose, the Kip Thorne, people like that, they were entered into this contest. And so I had my little work. I was just beginning graduate school, and I entered. Of course, I didn't win, but that was a great adventure for me. And so I wanted to do that finish my theory and investigate it for my dissertation. But my advisor, when I told him and brought my stuff in, and I told him I was trying to link electricity and magnetism, and when I first said that, he said, there's no connection. And so that was that. And then he told me, he said, if you try to work on something like that for your dissertation, it would be too controversial. You'll never get your degree. So he told me to work on it when I got out of school. So I've been working on it. So stay tuned to see the outcome. I know that was a long answer, but that was part of my story.
Oh, thank you. Thank you. That was wonderful. I love listening to your stories. And I want to thank you again for taking us all the way from the very beginning, the very big bang, all the way to the present day. You basically accomplished the mission of our conference from stars to cells. So I want to ask everybody one more time for a huge round of applause for our amazing first keynote speaker, Dr. Reva. Thank you.
Thank you.
Thank you, Dr. Williams.
Thank you, Jen. Thank you so very much, and all of you all.
Bye. Thank you.
Bye-bye.
She's amazing. Okay, so